Hey everybody, this is Stereo Police. I had a little time tonight, so I thought that I'd take the opportunity to begin a series of videos that I'd like to make on the new addition to the family here, which happens to be the H.H. Scott Stereo Master Type 222B Stereo Amplifier. And I figure I'd give you a little walk around, and in the next video, I'm going to hook this up to the bench here and get a look at the signals coming out of it, do a fast Fourier transform, find out approximately what its maximum power output is, see how clean the waveforms are, see how much it's distorting. We'll get a look on the Keithley over there and see what the THD is. Make sure everything is operating to spec before I hook it into my system, because I did purchase this pre-owned and reconditioned. So I have already listened to it on my test speakers, and it sounds darn good. But I haven't gotten a look under the hood yet. After I do my full set of tests here, I'm going to open up the bottom of it and get a look, and I'll show you that too. But I always like to know how things work, and I know you guys do. A lot of you guys do too. So let's get a look around the faceplate and get a look at the various tubes, and then I've already studied the schematic, and I'm going to introduce you to the amp, and I'm going to walk you through the theory of operation of the amplifier itself in plain language so that everyone can understand. These are very simple amplifiers. That's, I think, what makes them really beautiful, is just the utter simplicity of them. That's in part what makes tube amplifiers so fantastic, besides the fact that vacuum tubes themselves are such simple devices in how they operate. And vacuum tubes are also tend to be more linear devices than transistors as well, inherently, and require typically less negative feedback to correct distortion. So, and just by virtue of the fact that the inherent characteristics of vacuum tubes themselves lend to their own inherent qualities that people seem to like, and also the fact that they soft clip instead of hard clip. There's lots of reasons why vacuum tubes have the qualities they have, but it's also just the symbiotic design of the overall circuitry, the way the circuitry is. And I'm going to explain that to you, exactly how these things work. I have yet to hear this on a good system, but these are highly acclaimed amplifiers. People who have them love them. I can't wait for that day when I can take this out to my cottage and hook this up into a good system. Love to hear this through the Cornwall 3s. Looking forward to that. But for now, let's get a look at the amp, and then I'm going to walk you through the theory of operation. The specs I have on this amp is that, and I won't walk you through all these things, but it is rated at 13 watts steady state, which is pretty typical of the output tube, which is an EL84 output tube. And in class AB1, you would expect to see somewhere around 11 to 13 watts, 11 to 17, but about 13 watts is about typical of a class AB configuration in push-pull. And that is indeed what we have, and I've simplified the schematic for you. And I'm going to walk you through that in just a little bit, so don't be intimidated by the schematic, which happens to be upside down. But this is a very old but nevertheless typical class AB output stage with a center tapped transformer. It's how it's done. I'm going to walk you through this in just a little bit in a much more simplified version. I'm going to walk you through every single tube right here and what it does, all the way through the output tubes to the output transformer. We're going to trace a virtual signal on paper through, and I'll show you how it works. I won't cover the power supply or the rectifier. This is the rectifier tube. I won't cover that part. We'll just look at the audio signal. But let's get a look at the faceplate real quick. And we have, let me hit stop here and move this so I can get my hand on it. Okay, we have a loudness knob with a click for on off. And, you know, I really ought to unplug it because I do not want this thing to work. All right. We have a loudness with a click for on. Once it warms up, of course, you control the volume from here. And as part of the volume circuitry is this button here. And there's two positions. One says V at the bottom, the other says L at the top. That stands for volume and loudness. And the loudness is just like a, it does a similar thing to customary loudness buttons that you hit, where when you're at low frequencies, it'll emphasize the bass and the treble to try to offset the natural tendency of the human ear to de-emphasize bass and treble at lower SPLs. I never ever use that. So by putting it down at V, you turn that feature off. You turn the loudness off. And it's artificial. And I'd rather have a flat frequency response across the board. Again, by turning it up to L, you no longer have a flat frequency response at low listening levels. You have an artificially inflated treble and bass, or could be the opposite. You have a de-accentuated mid-range. Haven't studied the circuitry on that, so I don't know how that works. But I want that down to V because I want a flat frequency response. And then next to that, we have, and this is a beautiful faceplate, by the way, not a bit of patina on it. It's gorgeous. And then next to that, we have the stereo balance. And the left and right channels are labeled not left and right, but channel A and B. That's just how they did it. And these knobs are just, you know, smooth as silk. A very good restoration. The potentiometers are smooth as silk. And then we have the pilot light, indicating that the tube amp is operational. And below that we have a tape monitor for those who remember what those tape monitors were used for. I won't get into that feature, but that would be if you had a cassette deck or a reel-to-reel. To the right of that we have our bass control, and to the left, well, let me bypass that for a second. Well, I'll get into that right now. If you see right here is a good shot of our channel A, which we'll call that left, and channel B, which we'll call that right. And we have the individual ability to control bass and treble of our left and right channels. And in the middle we have a scratch filter, which is a high, a low pass filter. Basically a low pass filter. It'll de-accentuate high frequencies. All right. And to the left is our main stereo. Well, let's start with the input selector. We have a phonograph, our tuner, and our extra. Our extra would be considered by today's standards an auxiliary. So our tuner and our auxiliary inputs are essentially line level. That would be where I would input my DAC or my tuner. And phono would be for, in the back there'd be a high level and a low level input for RIAA equalized moving magnet. And I believe they have an input for ceramic as well. Back in the day there were ceramic cartridges. And then right there we have an equalization. There's an RIAA, and there's another equalization for tape that I'm not familiar with. And then our stereo selector. We can select the nature of the stereo we want. Now, I'm not familiar with all these features, but I can say that you can see as we have stereo, then we have reverse stereo, and then we can go down to channel A or channel B, hence the separate abilities to control bass and treble for channel A and channel B. So that's if we want to listen to one channel at a time for whatever reason. And then as we go over to the far left, we've got one for monophonic records, so we're going to convert our incoming signal, I guess, to mono. And then there's settings for balance A and balance B, and I really don't know what's going on there. I don't have an owner's manual for this. I can't tell you what's going on there. I've never had that feature before. Let's get a look at the back. Alright, as you can see, we have, starting on the right side, we have our magnetic high, magnetic low. I was using magnetic high for the left and the right channels, because I have this turntable that I was using has a moving magnet cartridge. I don't know what the magnetic low would be used for. Probably for maybe for those ceramic type cartridges. Probably for a lower input signal that's going to provide more amplification. Not exactly sure, forgive me. Maybe different types of cartridges. One had a low type signal, one had a high type signal, but it worked perfectly sufficient on magnetic high with my turntable. Definitely not an audio historian with these types of amplifiers, so I don't exactly know what was up with those. Maybe someone can tell me. Again, I don't have an owner's manual for this. I'm looking forward to getting one. There's our tuner input and our auxiliary or extra input. And this amp has the ability to generate internally its own center channel by taking the left and the right, or the A and B, and mixing them in a way to generate a center channel to fill in the space between the two speakers. I don't know if that was proprietary to Scott or if that was just a thing that was going on in the 60s. I think there was a time that there was like a Hafler effect, or I forget how it worked, where you would take the positive of the left channel and the positive of the right channel, in other words a different signal, and make that a center channel. I'm not sure if that's how they were doing it. Klipsch had a scheme as well, but not sure how Scott did it. And then there's this playback right there. Not sure what that is. I think that's for the tape monitor. Pretty sure that's tape monitor, but not totally sure. And then there's our speaker outputs, our various taps for the 4, 8, and 16 ohm speakers. Of course, with a tube amplifier, you've got to heed the taps based on the impedance of your speakers, otherwise you will improperly load the output tubes, which could cause major changes in how the in the sound, as well as possibly reducing the life of your tubes, or even causing a failure of the tubes based on drawing too much current. And of course, the zero tap is ground there, and there's an auxiliary power input, a fuse, and the power cord. And that's a walk around. And I believe these things came with housings, and I believe they were metal with louvers in it. I do not have one, nor do I want one. I believe that tubes need to breathe. They need to vent. They need to dissipate heat as efficiently as possible. So I don't want a cage on here, but a cage would be good if you had curious animals or children. But other than that, you know, a cage to a tube amplifier is tantamount to a grill, or, you know, on a speaker. It comes off when you listen. Just to prevent dust from getting on the speaker, and that's about it. All right, now let's walk through. I'm going to leave this in reverse, and let's walk through the theory of operation in terms that anyone can understand. I find this fascinating, and how simple this amplifier is. And we're going to start with where the signal starts. and trace it through from the exterior. Talk about how this tube amplifier works. These, by the way, are the output transformers. We'll get to those last. The mains power transformer is here. We're not going to cover this in detail, but of course the power would come in and feed the mains power transformer. From here, the primary would go in, the secondary coils would come out, and there'd be various taps for the heaters, for the heating elements of the tubes. That's what causes them to glow orange. And then one of the taps would go into the rectifier, which would convert the AC to DC, which we get filtered for ripple, and which would feed the plates of the various tubes. And there'd be some dropping resistors that would drop the voltages to what the tubes would require for their biases. And that's the DC part of it. Now let's talk about the AC part of it, the signal path. Let's look at the complicated real quick, and then I'm going to make it simple, so don't get intimidated by the schematic. The inputs are all over here, and there's of course a phonograph input with RIAA stuff. Not going to bother looking at that. But when we go from the inputs, and we'll choose, for example, a tuner or an extra. So where's the tuner or the extra over here? I think that says tuner right there. They're all going to go through the selectors, and ultimately they're going to come out right here. And the signal is going to go through 1/2 of a 12AX7, get amplified. We're going to have the bass and the treble. The bass and the treble circuitry is right here. The potentiometer is indicated there. The signal is going to go through the other half of the 12AX, get amplified, come out, go through this potentiometer here, which is the volume control. And again, I'm going to go back and redraw this simplified, so don't get intimidated by this. Come up through here, through this circuit here, which is a phase splitting circuit. So signal is going to come up through here, and one phase will come out to the plates of one of the EL84s, and then that same signal will come down to the grid of this triode here, come out to the plate in opposite phase, and come over here to the plate of the other EL84. And then these two will operate in push-pull through the output transformer, and the rest is history. Now let's back up and take this one tube at a time in simplified form. Okay, again, let's start out with pretending we have a signal coming from our DAC, and we just happen to want to put it into the extra RCA inputs. And we have our knob on the front selected to, our selector knob selected to extra. And our signal is going to make it over to the first of the 12AX7s. Here's one of many different types of data sheets for a 12AX7, and a 12AX7 is a ubiquitous, extremely common vacuum tube used, probably one of the most common vacuum tubes perhaps in audio history, used in vacuum tube amplifiers, at least in America, perhaps in Great Britain as well, maybe all over the world. And it's a tube that would be used in preamplifiers or in preamplification stages of a power amplifier. It's a low power tube, but it would be used in the voltage amplification circuitry of an amplifier. Not to provide high currents, but just to amplify voltage. And as you can see on the sheet here, it says service as an audio voltage amplifier. And looking at the little schematic of it, you can see it's two tubes in one. You know, each of these little symbols here, if I can circle it, that is a single tube right there. And to the left, that's another tube right there. The symbols you see there, that's a symbol for a plate. That's the symbol for a grid. I'm actually drawing this through the display of my phone, so forgive me. And then the symbol for a cathode might look like that. So that's a triode. It's got 3 electrodes, a plate, a cathode, and a grid. The cathode is the negative of the plates, charge of the plates. The plate is the positive charge of the plates, and the grid is what controls. It's like the valve, you know, it's what controls the flow of electrons from the cathode to the plate. So it's 2 tubes built into one. And that's why when you look at a schematic, you will sometimes see, as you do in this case, you will see, it's very small, but you will see it says 1/2 of a 12AX7 there. And you will see right there it says 1/2 of the 12AX7, even though they're drawn as 2 separate tubes. All right. I will note that for each channel there are 4 12AX7s used. There are 2 used in the preamplifier stage, and then there are 2 used in the phono. So there's 1 12AX7 tube itself used in the phono preamplification. We're not going to talk about that. And then there's 1 used in the preamplifier. So looking at this amplifier, the 4 tubes you see in the front right there, these 4, 1, 2, 3, 4, are 12AX7s. And we're going to pull that out. I don't know if you can get a look at it or not. Let me see if I can. I'm not sure it's focusing. There we go. And there are 4 of them. These happen to be General Electric. New old stock. I'll put that back in. And I like the fact that all 4 of them are all General Electric. They're all the same tube. So let's start tracing the signal. Our signal from our DAC arrives at the first 12AX7, or 1/2 of the pair. So here we are right here. I just drew this as a triode. So we arrive at the first half of the 12AX7. Our signal gets voltage amplified and phase inverted. When you apply a signal at the grid of a vacuum tube, you pick up that signal from the plate, it gets phase inverted. No big deal, but it also gets amplified. And then we go through a capacitor. The reason for the capacitor is we want to separate any DC that happens to be on the plate of the previous stage from the grid of the next stage. But the capacitor is very willing to pass the AC, no problem at all. So the signal goes right on in series to the grid of the next 12AX7. And it gets amplified again and phase inverted again. You see, I drew these out of phase, so this would be a larger version. So if anything, I kind of drew this, you know, this would look, you know, a little bit larger, and this would be way larger. Okay, so we went from here to there to there, and then we come to our volume control. I'm ignoring the bass and treble. We don't need to worry about that circuitry right now. We're just looking at the amplification. Then we come to our volume control potentiometer right here that we rotate to turn the volume up and down, and that was this guy right there. And as we rotate our potentiometer, which is like a variable resistor, if we were to bring it all the way up, we'd get the full signal. If we were to bring it all the way down, we'd be almost touching ground here. I'll just draw this as signal ground, and we get no signal. So As we rotate from the left position and start moving clockwise, we're moving the wiper up to get a higher and higher signal. That is our preamplifier stage. Done with the preamp stage. Now let's move on. Our next stage is our phase inverter. Now we've got to create, our output stage requires signals that are out of phase. This requires a signal that looks like that as the input to the grid of one of our EL84s, and the other EL84 as part of the push-pull arrangement is going to require an out of phase signal, equal in voltage but 180 degrees out of phase. But our starting signal right here is just this. So what we have to do is we have to create two signals that are out of phase relative to each other. And that is what our phase inversion circuit is going to do. That's what this guy does right here. So let's walk to that one next. I drew a simplified diagram of what's being done right here. And first let's note that these tubes are a 6BL8. And a 6BL8 is a pentode. It's a dual tube, two tubes built into one. And it's kind of unique in that one side is a pentode and one side is a triode. It's here or there why that's the case. It doesn't matter. It's beyond this. It doesn't matter for the sake of our discussion. But it's two tubes built into one. And in this particular data sheet, it said it's designed for use as a frequency changer in television receivers, but that does not matter. It's still a small signal amplification tube that's got the frequency response and the characteristics that are ideal for use as a phase inversion device. And here's how it does it. So we leave our volume control with a single signal that looks like this. And we go into, this happens to be the pentode, but I'm going to draw it as a triode. We go into the grid of our first 1/2 of our 6BL8. And of course we take our signal off the plate so it inverts the phase. I drew it as a phase inversion. And that happily goes right to, and this by the way does provide a little bit of amplification too. A little bit of amplification. And then this will happily goes right into the grid of our EL84. But remember down here we need a phase inversion to go into our other grid. So how do we get that? Well, our 6BL8 has another tube built into it. So what we're going to do is we're going to take that signal, bring it down here, and bring it in to the grid of that other tube. Take a tap off that plate, and when you tap off the plate, it's going to phase invert it. We've got our phase inverted signal, and that's going to go into the grid of our EL84. Now, the problem is this tube right here is going to amplify an already amplified signal. I'm going to call that A2 and A1 as an amplification factor. So we need to actually reduce this signal a little bit to compensate for the fact that this tube is going to do some amplifying. So we have a potentiometer right here to offset that or adjust that so that these two signals here become equal in amplitude. That's called our AC balance. It's actually an adjustment that has to be made to the amplifier on the bench by a technician. Let's go back and look. You can see clearly that's what's happening. Grid, our signal here, if you follow that, goes all the way to the grid of our EL84. Right here is where we tap that signal off, come down. I can't see, hold on, I'm sorry. Right here's where we tap that signal off, come down. I'm sorry I drew over top of it. There's our potentiometer. It comes down into the grid of the other half right there. There's the plate. We come over here up to the grid of the other EL84. So we've achieved our phase inversion. Here they are. So here was our 12AX7, and here's our phase inversion tube. By the way, I believe this system, if you want to look it up if you're interested, I think this is a version of what's called a paraphase phase inverter that was used on really old guitar amps. It's not exactly the same, but it's similar to it. So here is our 6BL8. This is an equivalent of it. 6UA 8A. So this is a substitute, but it's all the same. Let me see if I have if the other one's exactly the same. I like to have tubes that are. So this one, yep, 6U8A. At least they're the same. I want to have symmetry channel for channel. So we have that so far. All right. So now we're ready to go out to our output stage and take a look at what's happening there. Now we're ready for where the rubber meets the road. We're ready for our output tubes in push-pull class AB. Okay, once again I've drawn a simplified version of our output stage, and it consists of two EL84s. Now in the schematic diagram you'll notice that it calls for 6BQ5s. 6BQ5s, well, that is an EL84. There are different tube numbering schemes out there, and this is an older numbering scheme right here, but it's the same tube. And I had the first sheet of this data sheet, and I don't know where it is. Perhaps I left it on the printer, but it's a pentode, and essentially it's designed for audio use. It's an excellent little low-powered audio pentode, and very linear. It's coveted for its sound. It's a classic device, used a lot in hi-fi in the early years of audio, and still very much coveted for its sound. And lost the first sheet of it, but that's here and there. As you can see in the characteristics of it, this is the second sheet of it. In use as a push-pull class AB1 amplifier. That's just a class AB amplifier with enough bias to eliminate the crossover distortion. You can see that the maximum signal output power, we're looking at about 11 watts. So that's consistent with what I read to you earlier. What did it say? 13 watts? Somewhere in that ballpark. So that's consistent with what we have here in the Scott. And, you know, of course, if this was used as a Class A amplifier, it would be much lower, like 5 watts. And in Class A triode connection, as a triode, 1.95 watts, much less. Very low power. So you can see the efficiencies of using this in Class AB. You can get at least at 11 watts, which with a highly efficient speaker, that would be all you need. Okay, so on to the push-pull arrangement. Now, we've already talked about how we've achieved our phase split signals. Each phase split signal feeds the grid of its own EL84. So we came out of our phase splitter. We're going right into each of our EL84s. Each of these has its own output transformer. Each of these has its own output transformer. The A and the B channels are the left and the right channels. And the output transformer is center tapped. So you can think of this as each tube has its own transformer. You can kind of think of this as this tube's transformer is this, and this tube's transformer is that. You could almost look at it that way, but all together it makes one transformer. And I'll go into a little bit of detail right now in a second as to how that works, because I think it's fascinating. And I hope this is helpful. But ultimately, these two operating in push-pull will generate a high voltage, low, I'm looking at through my phone here, high voltage, low current signal. You could never ever drive a speaker with this. You know, this voltage would be too high and the current would be too low to drive a speaker. So we need an impedance matching transformer, which is what an output transformer does. So what this transformer will do will be to create a low voltage, high current signal to drive that speaker. And it's impedance matching because it'll trick these tubes into making it seem like this 8 ohm load is really something much higher, like 2,000 to 3,000 ohms through the windings. It's actually through the square of the windings. And that's beyond the scope of what's going on there. But what's really fascinating is, why did we need the split phase? And I do want to get into that. And I'll get into that as soon as we finish with the signal path right here. So once we provide our signal to the primary through magnetic flux, we couple the signal to the secondary, and the secondary feeds right on in. And the secondary has various taps, by the way. And let me draw that out. I'm going to draw a detail of the secondary. C, and it has various taps for the various impedances. Okay, so on the back we have the C, and that's going to be ground. And then we're going to have various taps for the 16, 8, and 4 ohm speaker impedances. I just drew this as one transformer, but that's what it's going to look like. And of course, that's what happens right there. Those are your connections to the external world. Now let's talk about how a push-pull works. I hope I can explain this, and I think I can do this in layman's terms. I'm pretty sure. So let's start out with the top side here with our inverted phase. Now these signals are inverted phase, but they're in sequence in time. So when a negative downgoing or negative cycle happens up here, at the same time an upward going or a positive peak happens up here. Same thing here. When these cross zero at the same time, and then when this is at a positive peak, the signal down here is at its negative most peak. So they're 180 degrees out of phase. Let's look at just the top one for now. So when this signal rolls down to the negative peak, the grid of this tube will be negative. And when the grid of this tube is negative, it's going to repel electrons. Okay, when the grid of this tube is positive, it's going to want to pull negative electrons this way. When the grid of this tube is negative, it's going to want to repel electrons and send them that way. That's why I'm going to draw the current accordingly. So when we're at this point here, negative, the grid of this tube is negative, it's going to send electrons in this direction, in that direction, and the circuit, this 350 is part of the circuit. So the circuit is going to go like this, like that. That 350 is the power supply, and you can consider this, just consider this right here ground. Just consider this right here ground. So each of these tubes is its own circuit. So we're negative going here, it's going to send a circular flow like this around this from the center tap of the transformer around the transformer. When this happens, the transformer is going to develop a positive voltage relative to the center tap up here. Because the transformers, the way this coil, this inductor right here in the transformer works, is it always wants to oppose the flow of electrons. And the way it opposes the way an inductor opposes the flow of electrons is it creates its own, look at it as a battery circuit. So if electrons are flowing this way, it wants to oppose them by creating a positive voltage up there, which is, in a sense, wants to cause current to flow the other way. Just view it that way. That's what's happening. So a positive voltage is going to develop up here. Now let's go down to the bottom. At the same time we had our negative voltage up here, we have a positive swing up here. Therefore, we have a positive going peak on our grid down here. If that's the case, instead of repelling electrons, we're going to be pulling them right through. So we're going to have this kind of flow in our circuit. And if we're going to have this kind of flow in our circuit, it's the same thing as up here. We're going to be developing a positive voltage up here relative to down here because our inductor wants to oppose the flow. Look at what's happening overall right here. It's like having two batteries stacked on each other. They're adding up together. And by adding, and the transformer is imparting that to the secondary as a negative and a positive. The two are stacked. So what we get in simple form is our signal added together like that as a hump. Added together. That's one way to look at it. Now all we've done is we've amplified the first half cycle. From there to there, and there to there. Now the reverse happens. Let's look at the second half. Now we're going to amplify from there to there, and there to there. It's exactly the opposite. Now our positive signal is on the top EL34. Because our grid is positive, we're going to be pulling, we'll call that ground. We're going to be pulling electrons from our ground all the way around that way. Our coil, our inductor doesn't like that, so it's going to oppose it by developing a positive voltage down here relative to up there. So call that our battery, for lack of a better word right now. Let's go down here. At the same time we had our positive going peak, we have a negative going peak down here at exactly the same time. We have our negative on our grid. Well, our negative wants to repel electrons from our cathode, so it's going to push electrons that way. Well, look what happens in our coil right here. Same thing. Our electrons are flowing this way. Our coil wants to oppose it by creating a positive voltage here and a negative voltage there. Look, completely the opposite. It's like we have two batteries stacked on each other with the negative down here and the positive up there. And what we end up getting is we end up completing the waveform right there. So that's our push-pull circuit. And it's called push-pull because, well, whenever one tube is, you can consider this pushing, the other tube is pulling. So if we consider starting from this tap of the transformer as pushing electrons into the transformer, well, look what's happening down here. We're not pushing electrons into the transformer, we're pulling them out of the transformer. So this guy's pushing electrons into the transformer, this guy's pulling electrons out of the transformer. That's called a push-pull output stage. That's how it works. Pretty simple. I hope I was able to do that without being too confusing. And here they are. Here are the EL84s. Let's pull one of those out. Well, let's pull them all out. Let me make sure they're all the same, because I have not done this yet. Let me read it. This is Amperex 6BQ5. So this, oh, see, it's got both on there. It's a 6BQ5. It also says EL84. It says made in Great Britain. So that's an Amperex. And the other one next to it in the same channel is a Raytheon. So we've got a mix of two of them. I generally don't like that. So I've pulled out that channel there. Let's look at the other two. Well, I can tell you without pulling those two, well, I'll go ahead and pull them out. This one here is a Scott. So this is an original Scott right there. And then this one here is an original Scott. Let's see what it says. It says EL84 6BQ5. So one of my channels has two original Scott tubes, the other has a mixed bag. I really don't like that. I'd rather have 4 identical tubes. But I'm going to go with it for now. But I'd much prefer to have 4 identical tubes from the same manufacturer and from the same era. That would be my preference. But when you change tubes in this amplifier, there are 2 adjustments. And I'm coming to an end here, but there are 2 adjustments that need to be made. In the phase splitter, you've got to adjust the AC offset. And then right here, you've got to adjust the DC offset as well. Which the AC offset's pretty straightforward. I'm not sure how to do the DC exactly yet. I'm still working on that. But I just want to listen to it for now. Not ready to get into that yet. So there you have it. I hope that was helpful. This is a marvelously simple amplifier, but there's beauty in simplicity, and sometimes the simplest things are the best things. The power supply is simple, the circuitry is simple, very few gain stages. As I mentioned, the 12AX7s are gain, a tiny bit of gain in the phase splitter, and then your output. And the reason it's called a power amplifier, by the way, is these 2 stages right here amplify voltage. I'm going to pretend that the phase splitter doesn't amplify anything. The output stage amplifies current, and power equals voltage times current. So The output of an amplifier is your voltage times your current is power. So you need both to get power amplified, and that's what a power amplifier does. So without the output stage, you have a voltage amplifier. Without this stage, you have a current amplifier, but with both, you have a power amplifier. All right. In the next video, I'm going to take apart the bottom cover and let's get a look inside of this beauty and see what kind of workmanship was done to it. I have no idea. Hope you found that enjoyable. Ciao.